and record to the cloud this time. So if my computer dies, we'll still have it.
Good idea.
But anyway, it's 3:05, and maybe everyone is here, so we can.
Okay, so just as a reminder, our goal is to work towards having a working interpreter for a real language that can actually do computation, unlike what we did last week. And more importantly, it can do computation in a way that you understand. So hopefully by the time we're done, you'll have some understanding of Haskell. You'll be able to write a real program in this language, and maybe it'll do something, maybe not something useful, but maybe it'll do something, So we're basing this language off of one of the versions of CS421, which is the interpreters class. It's also required, so you're going to have to take it eventually, so you're getting a huge head start here, yay. And the class is taught by two different professors. Right now it's being taught by Professor Maddox. He teaches it in Haskell, and he teaches it very differently from the other professor, which is Professor Gunter. She teaches it in OCaml, and the way that she teaches the class is she basically draws this tiny circle around portions of programming languages. And then she talks about everything in that tiny circle in a huge amount of depth. And so what she does is over the course of the semester, students implement an interpreter for a very simple language. We're basing our language off of that one. It might end up having, a few more features or, some syntax sugar for nicer things. You'll see what I mean in a little bit. So right now, since we haven't finished our own implementation, I'm just showing you guys the reference implementation of their interpreter from that class. So this language is called picoML. The name comes from a family of languages called ML languages, which were kind of like the first functional languages that people really used. OCaml is also part of the ML family. And so slightly different from Haskell, ML and picoML, not indentation sensitive. So you can see here, I actually already messed up. You need double semicolons to terminate your lines. So, 0 double semicolon, result is 0, as you would expect, it evaluates to 0. Constants are constants. True, also a constant. You can use it like a calculator. So you can say 5 plus 5, you get a reasonable answer. You cannot add a floating point number to an integer. And we're hoping that our interpreter will give you a slightly better message than does not type check. Hopefully it will say why it doesn't type check. But yeah, so the reason for this is that the plus operator specifically takes 2 integers. And I said specifically 2 integers, that's actually true. You can't even do this. This doesn't type check either. So if you want to add floats, you actually need a different operator, and this will work. Okay. So it's, I don't know what the right phrase for this is. There's no partial polymorphism, right? For every function, either it works at exactly one type, like this plus operator works only for ints and plus dot works only for floats, or it works at every single type you can imagine. And obviously it doesn't make sense to add Booleans, so plus can't work on more than one type. It only works on integers, okay? The language does have polymorphism. So for example, if you have a question, you should just interrupt me because I can't have the chat open on top of all the other windows that I have for what I'm doing.
Actually, I just want to comment real quick. The word you're looking for is ad hoc polymorphism.
Yeah, okay, thank you. Yeah, so unlike Haskell, where we can overload operators so that they do different things at different types, we can't do that in ML. Okay, I had somewhere that I was going to go with this and then I forgot. Oh yeah, so we can make a polymorphic function. So, wait, is this the right way to do this? I think it's let id equal fun x to x like this. Yeah, and so this function is polymorphic. We can say id true, and this type checks. We can also say id 5. This also type checks, right? So, so here we're using it at Boolean. Here we're using it at int, and these both work fine. And in fact, we can use it at any type, and it will work. So that this is a truly polymorphic function, right? And also you can see, up here we had things that weren't type checking, which means we have a type checker. You might also notice I'm not actually writing any types, and things are still getting type checked. So the language has what's called total type inference, which means if a term does type check, you can identify the most general type for that term in every case. And there are actually some cases where, for a particular reason that we'll talk about later, we choose to infer a more specific type than we would otherwise. But it is possible to infer the most general type. And so the syntax of language doesn't even support writing type signatures. If you write a type signature, you get parse errors because the syntax doesn't support that. If you wanted to add the ability to add type signatures, you could. It's an interesting exercise, but it actually makes the type inferencer more complicated. So we're probably going to stay away from doing that here. Okay, so the other thing is a syntax note. You can see to introduce a new binding, I used this let keyword. And then I ended up with a new binding in my environment, id, which I could then refer to later. So we didn't have that in simply typed lambda calculus. And then this syntax for creating a function, you'll notice was different from Haskell. I couldn't write, whoops. I can't write this, right? This doesn't parse. So this is one of those things that I said, maybe we'll add syntax sugar for this, which means you write this and then the interpreter just automatically translates it into this for you. That's called syntax sugar. Haskell used to do this, it doesn't anymore. What Haskell does now is kind of complicated and confusing and way outside the scope of these workshops, but it did used to do this, so there's that. This fun keyword is kind of like a lambda in Haskell. I don't remember if we introduced lambdas, but maybe not. So fun creates an anonymous function, and then the let binding assigns a name to that anonymous function. You can also do other things. You can say, let x equal 5. Now if I refer to x, I get 5. You can say, x plus 5, just like you would expect. But x is an integer, so you can't say x plus floating point 5. Doesn't type check. The other thing is, this might take me a second to write because I always get this wrong. If you tried to write, say, a regular factorial function, let's see, did I get this right? That looks right. Yeah, so this doesn't type check. And actually, it's a little bit worse than that. The reason that this doesn't type check is because fact isn't in the environment at the point that we're trying to use it. So let bindings are not recursive. If you want a recursive binding, the syntax is actually different. So you have to use let rec like this. And now you actually do put one argument here. And now it's if n equals 0, then 1, else n times fact n minus 1. This should type check. Yeah, and you see up here when we defined id, it said closure. Now it says recvar. We're actually not going to do it this way. We're going to use closures for both of them. The particular reason that this class does it that way is because it's much harder to construct recursive closures in OCaml than it is in Haskell. In Haskell, it's actually super easy. I'm not even going to, or I might, but I could do it without even pointing out that something weird happened and you might not even notice. Like, it's so easy. But anyway, so now this function works like you'd expect. You could see it was even pretty fast. So it behaves just like a regular function, but it's a recursive binding. So I think that's most of the things. Oh yeah, also there's string constants. Whoops. And there's also like print, so you can, oh wait, I guess you have to print strings. Is that right? No, okay, I don't remember. I'll look it up later. But yeah, so we're not going to get to this stuff today, so that's fine. We'll come back to this in the future. I don't remember how to quit either, so we're just gonna Control C that, okay. So I think I can go on to writing code. Did anybody have any questions just about that? I guess I should have left it open, but.
Wait, so the reason that the direct recursive one doesn't work is because it's like not lazy, right? So fact isn't defined in the environment at that point.
It's not that it's not lazy. Yeah, it's that the let binding isn't recursive. So when you have a let binding, right, you say let variable name equal expression in body, right? And so inside the expression, the variable name is not in scope. Whereas in Haskell let bindings, it is, because Haskell let bindings are recursive. So if you want a recursive let binding in picoML, you have to ask for it explicitly.
Yeah, okay.
And we will probably keep that feature in our interpreter, just because for low level or at least strict functional languages, that's actually normal. Even though we technically don't have to, we're going to make recursiveness opt-in. Actually, that's a good idea anyway, because it lets me point out the difference between the recursive ones and the non-recursive ones. So yeah, I think we'll do that. Anyway, okay. So now I'm going to pull up editor. Okay. And so what we're going to do today is we're going to implement, hopefully if we have enough time, a complete interpreter that only accepts constants. So it can't actually do computation, but you can enter constant values and it'll print them back to you, as well as their types. Okay. So we're drawing a tiny circle around an easy part of the language, implementing the whole thing, and then we'll add new features to the language by adding them to the whole interpreter. And so at least, you know, that makes expressions super easy. It's even easier than it was last week. We just have constants, and I'm just going to stick deriving equals and show onto every data type today, even though we're probably not going to use them. And so, okay, what are our constants? We have integers, we have floats. We're just going to use high precision types because we can, and for no other reason, and we have unit. So even in functional languages, we have unit. I'm going to leave off strings for now because we are going to talk about parsing today, and parsing strings is a little bit harder. But we'll get to that. Okay, yeah, so like I was saying, we had unit in our simply typed lambda calculus last week. We're still going to have it in our higher level functional languages. You know, even Haskell actually, Haskell actually has unit too. It's written like this, and the type is written the same way. So this one's a value, this is a type. And it's useful sometimes. It's actually in the reference code, so we'll see it later. So just having a type that only has a single value of that type is actually a useful thing. And so we will have that in our language. And okay, speaking of types, we only have constants. So what types do we have? We only have type constants. And for reasons that we'll get to much later, we're not going to use an enum type for type constants. We're going to leave it as a string. And so we're, for example, the type of int is tyconst int, like this. Okay. And the type of Boolean is tyconst bool, etc. And you know, all of these things are going to get more complicated as we add more features, but that's okay. And then the one other thing that we need is what are the actual results? So the results of an evaluation are called values. And the only values that we have are kind of the equivalents of consts. So we have int values, we have float values, we have bool values. I don't know why I lined those up, but I'm not going to fix it. And deriving each show because I'm doing that for everything. So these are all of the types that we need for now. Okay. And again, you know, as we add more stuff, there will be more values. We'll have function values and string values and stuff like that. So the next thing in my file is parsing, but I think I'm going to do evaluation. Or actually, let's do type checking first. Parsing is a little bit harder to talk about, so we'll do that later. So, okay, this is stuff that we talked about last week mostly. So let's just put a section header. So none of this should be super new. So for now, our type checker is super simple. It's not possible for type checking a constant to fail, so we're not going to pretend like it is. There's only one expression type. There's only one type that we can return, which is tyconst. And now we just have to decide what string are we using. And so if we have an int const, we don't care what's in it. Type is int. If we have a float const, we don't care what's in it. We have float. If we have a bool const, we don't care what's in it. We have a bool. And if we have a unit const, we don't care what's in it. We have unit. We're going to write out unit in this language instead of using the open and close parentheses. And this is a whole type checker. We're done. Right. So again, super simple, small language, constants only. Nothing we do today should be super hard, which is good because it means I have time to talk about parsing. So are there any questions about this? Actually, I'm not sure if I introduced this last week. The $, you can see, oh, actually, maybe don't look at the type at the bottom. That was way scarier than I was expecting it to be. The $, is basically an operator for function application. So if you go into an interpreter and you ask for the type of this, it'll respond, oh, why did it do that? It'll respond that its type is function from A to B, something of type A, something of type B, right? So this is just function application, right? Function on the left, argument on the right, apply the function. That's exactly what function application does. The benefit is that a case block can't be an argument. So this is giving me a parser, and this lets me make the result of the case of block the argument of tyconst, okay? So I think I didn't use $signs last week. I'm gonna use them a lot this week.
Can I just jump in? So you could use parentheses, it would just look super gross.
Oh yeah, that's true. So the other option is you put a parent here and a parent here, and that's really ugly. No one actually does this in real code. And the Haskell compiler is really smart. There's absolutely no cost to doing this. The Haskell compiler knows that it can just replace this with a regular function application. So there's no cost. So, okay, were there any questions about that? Doesn't sound like it. Okay. Again, if you have a question while I'm writing code, you can just interrupt me. I will put a few more comments like this just with types of operators in here, especially when we're doing parsing, because there's some weird ones. This is weird. I still don't know why it does that. Okay, so let's do evaluation. And okay, what does evaluating do? It takes an expression, it turns it into a value. Based on, up here, you can see our expression and value types, right? This is going to be, only slightly harder than type checking was. So let's do the same thing. Only expression type is constexp. And what do? We inspect the C, look at what it is. If it's an int const, we return an int val. If it's a float const, we return a float val. It's not float value, is it? Oh, that's a typo. Oops. Okay. If it's a bool const, we get a bool val. And if it's a unit const, we get a unit val, right? So pretty simple. Vertically aligning arrows like that is a somewhat standard Haskell style thing. Emacs can do it for you. I thought that VS Code could do it for you, but it turns out that it actually can't. I think they're working on adding support for that. But yeah, most Haskell developers just align the arrows because it looks good. So okay, that's actually type checking and evaluating. So in terms of what we did last week, this was even easier. We've already done everything for this tiny useless language that we did for simply type lambda calculus last week in an hour, and we did this in 5 or 6 minutes. So today we're actually going to do a little bit more. We're going to talk about parsing. Parsing is actually one of the trickiest parts of making a new programming language, like figuring out how to parse it correctly, how to reject things that shouldn't parse at the right times, as well as accepting things that should parse, can be very tricky. And making sure your parser is like efficient, that it doesn't run into like really bad time complexity, can also be super hard. So just to check, I don't know what year everybody is in. Has anybody not taken 374? That's probably most of you.
Oh, I haven't.
Yeah. Okay. No. Yeah. Okay. I would expect that most of you haven't. So, are you guys familiar with the idea of backtracking?
Like in algorithms?
Yeah.
Yeah.
374 is the algorithms class.
Okay.
Yeah, so the idea with backtracking, recursive backtracking specifically, is you just kind of make a guess and you assume that the guess is correct. And then you keep trying to solve the problem, assuming that you made a good guess. And then if you later find out that your guess was wrong, you backtrack your algorithm's control all the way back to the point where you made the guess, and then you make a different guess. And then you just keep doing that until you've exhausted all of the possible guesses, and eventually you'll find the one that works, right? The problem is backtracking is really slow, right? Every time you make a guess, your algorithm potentially has to try that many possibilities. And since it's making guesses on top of other guesses, like you make one guess, you go a little bit, do a little bit of work, and then you have to make more guesses, right? The number of guesses that you're actually making scales exponentially with the input size of the problem. So when you're writing a parser, if you're not careful and you use backtracking where you shouldn't, you can get exponential time complexity, and that's unacceptable, right? I've actually written an interpreter before where I made that mistake and I did some backtracking where I shouldn't. And then I tried to parse a like 20-line program and it took 2 minutes, right? That's just not okay, right? No one will ever use your language if it takes 2 minutes just to parse the thing. So this language right now is super simple, and there actually wouldn't be anything to mess up with backtracking here, but as the language gets more complicated, it'll be a real concern. What people would normally do is they would use what's called a compiler, where there's some special syntax, and you use that syntax to specify the syntax of your language. And then the compiler generates two things for you that do the parsing for you. We're not going to use these because we don't want to introduce more syntax on top of the Haskell syntax that we're already introducing. But just that you know, this would be the normal way to write a parser. So the first tool you get is called a Lexer. The Lexer breaks up your input into what are called tokens. So for example, earlier when I was writing some code in that interpreter, you write 5 plus 5, you get 3 tokens. So the first token is a number, it's the number 5. The second token is the symbol plus, and the third token is the number 5. And that's all the information that you get. The Lexer doesn't know that plus is a binary operator. You know, it doesn't know anything about plus other than that it's a symbol, because the character plus is a symbolic character. It might actually work out that the number is 5 instead of that it's just the character 5. So like if you write 55, it might work out that the number is 55 as opposed to just the string 55. But that's basically the most information that you'll ever get out of a Lexer. The other thing that you get is a parser. So the parser takes an input stream of tokens and it arranges them into a tree. And the tree is called the abstract syntax tree of the language. And then that's basically our expression type. And then you would go from there. And in most languages, interpreters and compilers, you would actually have an intermediate type. So you would take the expression, you would turn it into something simpler, and then you would work on that instead. Our expression type is going to be so simple that that's not worth doing, but just that you know, that's pretty normal. So, okay. Whoops. So in order to do parsing, we're going to use a library called Parsec, which is super old. And it was actually one of the first reasons that people started using Haskell, because this library is so good that parsing in Haskell was just so easy that people were like, okay, I have something that I need to parse. I'm going to use Parsec. So first I need to import it. I'm going to hide the function that's actually called parse because I wanted to find my own function called parse. But I do need to use that one. So I'm just going to import it and make it harder to refer to. So this is called a qualified import. This lets me refer to the name parse imported from the Parsec library by doing this instead of just parse. Okay, so I'm gonna do that later. And then I need one other import because we're parsing strings specifically. So I'm gonna import text parsec string. So this is just like, I want to use Parsec to parse strings. There are other ways that you can represent data. Like I said, you could have your own stream of tokens, for example. And there are other text types in Haskell as well that we're not talking about. But Parsec does work with them. So, okay. The way that the Parsec parse function works is its first argument is a parser, and then it needs a source name. So we're going to make our own parse function. On top of that, we haven't written any parsers yet, so I can't put anything there. And then we'll just say the source is interactive because we don't have a way to read from files. And the type of this function is going to be, it takes a string, the input, and it returns either a parser or an expression. I talked briefly about either last week after the time was up. So this is how either is usually used. It's used to indicate failure. So either we fail with some particular error, and these parse errors are actually really informative. I'll try and show that later. Or we succeed and we get an expression back. Okay, so now what we have to do is we have to write a parser. And so actually I'll just put this here. We want to call it parseexp. Okay, and so parseexp has the type parser expression. And this looks a little weird. You would think, you know, what is a parser, right? A parser is a function from a string to a result in, you know, like this. In some very complicated way, a parser is a function from a string to a result. And the particular way that Parsec works is actually not super complicated, but we haven't talked about enough Haskell to really understand it, so I'm not going to try and explain it. But basically, this parser type is just hiding all of that magic behind. So, you know, somewhere in Parsec, they've defined, they've defined something like type parser, parser A equals really complicated thing in terms of string and A, right? And parser is baked to string. So I got parser from importing text parsec string. There's a more general thing that I could have used instead, but you know, why would I do that? I know I'm parsing strings. Okay, and so the idea is, and this is why I mentioned backtracking earlier, we're writing a parser with a strategy called recursive descent. So at every point, we're going to make a guess about what we think we're going to see next, and then we're going to proceed as though that guess was right. And so first of all, to parse an expression, the only type of expression that we have is constexp. So I'm going to use a new operator here, and then I'll explain what it means in a minute. And now for parse const, we have a parser that returns a constant. And so now we want to try recursive backtracking. There are several possibilities that we could see for a constant. So for example, the first one is we could see the string true, right? And when we see true, I'm going to use another operator that I'll explain what it means in a minute. And I also have to go and import it because I forgot. We want to return the Boolean constant true. So you can already kind of guess what these operators are doing just from how I'm using them. Okay, so now the thing is we have this one thing here, right? So this is one possible constant. But what if we were wrong, right? What if we start looking at it and we discover that our guess was actually wrong? The next character isn't T. We want to try something else. So the operator that we use for that is this thing, which is, it's pronounced alternate, but no one ever actually pronounces it. You can also just read it as choice. And so now, okay, what else could we have? We could have the string false, right? Which is a false Boolean constant. Okay, and so whenever we have choices, we express them using this operator like this. We write a parser for each choice, and then we separate them with this thing. We'll keep going in a second. I want to talk about these operators that I've been neglecting. So, okay, what we have here is we have a parser that parses a const, right? We want to turn that into a parser for expressions, right? So what we want is a function from parser const to parser exp, right? We want this. What we have is we have two things. So we have a parser const, and we have a function from const to exp, right? This is the const exp constructor, right? So we have both of these things. What we want is this thing. This operator lets us do that. So it takes the function from const to exp and it lifts it over a parser. So we get a function from parser const to parser exp. Does that make sense? This is actually a super general operator. We're just using it specifically for parsers here. So if you're familiar with languages that have like a map function, like Java has .map for lists, so does Kotlin, Python has it, C++ has it in the in one of the headers that I'm forgetting the name of, probably algorithmic, maybe functional, I don't know. So this is a pretty normal thing for languages to have. In Haskell, map is specific to lists, but this operator is an alias for fmap, which is the more general version. And it turns out to be super useful. So, okay. Other cases, we have unit. Oh, yeah, and I neglected this operator too. So this operator just says, parse this thing. So, you know, the result of this is a parser string. It returns the string that it parsed. But then it says, I don't care about the string. I want to return this thing instead. So that's all that we're using it for. Okay, and then the other case is parse number, which is going to be a little bit more involved. And the reason that parse number is a little bit more involved is because of the backtracking thing, right? I could say parse some number of decimal digits. And if it ends there, then it's an integer. Or alternatively, parse some number of decimal digits, and then if the next thing is a dot, parse more decimal digits, and then it's a float. But instead of doing those separately, I can just do them together. So we're going to write a function that, we're going to write a function that decides to do that on its own. We're going to use a few new combinators, which is an idea that I want to introduce. So in functional programming, in general, so this isn't something that's specific to Haskell, it's very normal to put complicated things together out of smaller things. And recursive descent parsing, did I say that wrong? It's normal to put big things together out of small things. And so recursive descent parsing specifically is like really, really big on this. You can see we're building a big parser out of a lot of smaller parsers. And so one family of things that's really useful for doing that is called combinators. And how they work is they take a parser as an argument, they return a new parser as a result, and they use their argument parser to do something interesting. So for example, sorry, this should be integer part. When we parse a number, we're expecting to see many digits, except we want to see at least one. So I'm going to use many one instead of many. That's the only difference, right? And so this means many one is a combinator. It takes a parser as an argument and returns a parser that parses that thing and then parses it again and then continues to parse it until it runs out. And this parser only fails if there weren't any digits there to begin with. So this will give you the integer part of a number. And now, okay, well, what about, actually, okay, let's do this and then I'll come back to it in a second. I'll also explain what do means in a moment. I just realized I forgot that. Okay, so imagine we were only parsing decimals, right? We would, or actually, I guess I can explain it now. Do makes things happen in sequence. So this is saying parse many one digit, bind the result to integer part, then parse a character, and then parse, let's see, what would we do after that? We would parse the decimal part, which is many digit. And the reason that this one isn't many one is because in the syntax of our language, you could write, say, 1 dot, and that gives you the floating point number 1.0. So there doesn't actually need to be any digits here. So you could do this, and this would give you a floating point number, or at least this would give you the parts of a floating point number. And then you need to put them together. So you would return a float const, and now I'm going to use read to turn a string into a double. So if we look at the type of read at the bottom here, read is basically a parser in its own right. So read takes a string. I made it go away. Read takes a string and returns something that can be read. In this case, a is double. And what do we have? We have the integer part followed by a dot, followed by the decimal part. And then I'm going to stick a 0 on the end. And the reason that I'm going to do that is because read uses Haskell syntax. And in Haskell syntax, you cannot write 1 dot and expect that to parse as a double. That's just a parser in Haskell. So sticking this 0 on the end doesn't affect numbers that actually have a decimal part. But if you didn't write a decimal part, then it inserts it for Haskell. So this is just to help Haskell's read function. Okay. Anyway, this works. The problem is, what if we didn't see a dot, right? What if we just had an integer, right? So if all we had was an integer, this is actually a problem because once we've chosen to parse number, we can't parse the integer part and then give up and proceed as though we actually parsed an integer and go from there. If we start parsing a number and we parse an integer part and then we see that there's no dot and we give up, we're giving up completely. We're backtracking all the way to the point where we decided to parse a number to begin with. And that's not what we want. So what we actually want to use here is we want to use another combinator that makes this part optional. And so I'm actually going to join these lines and use a slightly different syntax. I want to get rid of this and this. So this, this syntax kind of does the same thing as do notation. This says parse a period, then parse many digit. Okay. And then I'm going to name this decimal part and I'm going to stick all of this inside option maybe. And so option maybe says take this thing, the argument. Remember, it's a combinator. So the argument is a parser. Option maybe says take the argument parser. And then if try and run that parser. If the parser fails, don't give up. Just return nothing, right? So we've talked about maybe last week. If the parser fails, just return nothing. If the parser succeeds, then give me just of the result. And so now we actually have a way to decide whether we have a decimal part. And so if we have nothing, there's no decimal part. Well, then what we have is an int const, and we'll just read that. Now we're using read to turn a string into an integer instead of a string into a double. If we have just of some decimal part, well, then we do the thing that we were already doing, except instead of decimal part here, I need to use D. Okay, does this make sense? That was a lot of stuff, like relatively fast. So if anybody has any questions, I can spend the rest of the time answering questions. That's totally fine. Or if you're like totally lost, speak up and say where you lost me and we can go back to there as well. Okay, seems like everybody's following. That's good. So yeah, this is a lot of syntax. A lot of stuff going on. So just a reminder, it's probably obvious what this arrow does from how I was using it, but it says run this parser and then bind the result of the parser to the name integer part. So if we look at the bottom, we can see integer part is a string, right? List of characters, the same as string. And here, decimal part is maybe list of string, right? So again, note the type of this whole sub-expression is actually super scary, but it's parser maybe string. Right, so let's see. If I go back here, oh my gosh, I can't type, dude. Okay, if I go back here, put parentheses around all of this. This is parser maybe string. You can see it's not giving me any errors, so it likes that. But decimal part drops the parser, right? So it just binds decimal part to the result of the parser, but not to the parser itself. Okay, actually I should just undo. Okay. And we're going to use these arrows a little bit more when we get to the REPL. And I say get to it as though it's not the next thing. These arrows are just the regular case of arrows that you're used to. And then return is special. I don't want to show the type signature because it's too general. But return isn't the same as return in other languages. So for example, if I go right here and I say return in const 0, which is obviously wrong, right? You can see that this compiles, right? Orange isn't an error, or orange is a warning. But if I read the warning says redundant return. Well, that's confusing, right? If I had used this return in a regular imperative language like Java, this would just exit the function immediately and return in const 0. But that's not what's happening in Haskell. And return is actually a bad name for this function. And people have been suggesting for many years that they change it for precisely this reason, because it makes it sound like it does something it doesn't. All that return does is it takes a value and it produces a parser that parses nothing and always returns that value. And the reason that this is useful is at the end of a big parser like this, right? We've done all our parsing. All we need to do is turn the string into the actual value that we want to return. And so we use this return function. And so, in this case, the word actually looks reasonable. This is a reasonable word to be using here. If you're one of the people that thinks this is confusing and you don't want to use the return, the alternative is pure. So you can see this also compiles. Pure and return are synonyms. They're actually usually, one of them is usually defined as the other one. So in this case, they probably wrote return equals pure somewhere in their code. And so yeah, pure is actually slightly more general, but like honestly, who cares, right? For all intents and purposes, they do the same thing. And so here it's a little bit more obvious that all we're doing is returning a parser that does nothing and then produces this int const. So okay, I'm going to leave it as return just because I'm not one of those people that thinks return should be avoided. But yeah, there are other languages that were inspired by Haskell. Oh, whoops, wrong keybind. That use like basically Haskell syntax for everything, and they don't have return. So one example is Idris. If you're super into type theory and you like dependent types, Idris is trying to be a general purpose programming language with dependent types. And it's doing okay at that, but it doesn't have the ecosystem yet, so it's hard to use. Idris works a lot of the same way that Haskell does with all of this stuff, and it doesn't have return. Return is not a function in Idris. And by that, I mean, if you write return and you use a certain compiler flag, the compiler will replace it with pure for you and then shout at you for not using pure. And that's only to be helpful to people that are coming from Haskell. If the designer of the language had had his way, it would just be an error. Anyway. So the last part we're going to do is
move on. Can we just really quick see the parser like running and do something? And
yeah, that's a good idea. Okay, I wasn't planning on doing that. So I'm only sharing the window, right? You guys can't see my reference code. Okay.
Yeah.
So let me switch to sharing my whole screen, and then we'll. Oh, you guys are going to see yourselves. Okay. Enjoy. I can hide that maybe. Can I hide that? Yeah. Okay. I'll hide that just for now. Okay. So let's load this up. Okay. So one thing that I said I wanted to do was I said the parse errors are pretty informative. So this is what I mean. This left isn't part of the parse error. This left is here because we got a parse error, and the constructor for either, in this case, that contains a parse error is called left. So this is part of the either. The parse error says, at interactive line 1, column 1, there was an unexpected open square bracket. Okay, that's true. But then it goes even further, and it tells you what it would have accepted. It says it would have accepted true, false, unit, or a digit. So, okay, let's try that. Parse true. And we get, so right again is here because of the either. We get a success, const exp, bool const true, okay? We can parse false, we can parse unit, and then we can parse numbers. So we parse 0, we get an int, we parse 0 dot, we get a float, we parse 1,000 dot, we get a float, 1,000 without the dot, 1,000, So pretty much exactly how you would expect integer and doubles to parse. I mentioned when I defined these that these are high precision types. So you can get as much precision out of these as you would normally get out of a floating point number. I'm probably going to get this wrong on my first guess, but I think that many. Yeah, so this is a normal problem with doubles. If you have too many zeros here, it still parses, but the type doesn't have enough precision to represent this one, and so it just disappears. There's nothing that you can do about that as a language designer. Integer, on the other hand, this is not a 64-bit int type. This is actually infinite precision. So you could write an arbitrarily large integer and it will work. We didn't have to do that, but I thought it would be fun. If you only want 64-bit ints, then you would use int instead of integer. That's just a Haskell thing. So okay, any questions about the parser? There's nothing like super magical, but it was a little bit involved for the first parser. that you've probably seen. So, okay, if there's no questions, I'll go back to the REPL. Or sorry, not back to the REPL, back to the code. So, okay. For the REPL, if you looked at the reference code from last week, it's probably going to look mostly the same. Yeah, I'm going to use this do notation again. This time I'm not using do to make a parser. This time I'm using do to make interaction with like the outside world, interaction with the user. So, okay. A REPL has, I mean, you know, 4 parts. REPL's an acronym. So R is read, E is evaluate, P is print, and then L is loop. So first, for read, when you read in a line from the user, you get maybe an expression. So REPL read does parsing. The reason I'm putting maybe here is actually not because the parser can fail. If the parser fails, REPL read will just keep trying until the parser succeeds. This maybe is in case the user types quit. So if the user types quit, we don't want to return an expression. We actually just want to exit. There are some cleaner ways to do this once the language is more fleshed out and like has error types, but the language doesn't have those now. So we're not going to bother. And okay, the first thing we want to do is we want to print a prompt. So I just went over to my reference code because typing Lambda is hard. So, okay, what does putString do? PutString takes a string and it, no, stop complaining. It takes a string and it prints a string to the terminal for the user to see. Oh, oops, sorry, okay. And it doesn't print a new line after. So there's a different function, putString line, that prints a new line. We don't want that, right? Prompt goes on the same line. Okay, and then what do? Then we read a line of input from the user. So getLine does that. And again, this arrow here is doing the same thing it did in the parser. This says execute something that interacts with the outside world, in this case, reading from the terminal, and then bind line to the result. Okay, and then we're going to look at what line is. If line is specifically the string quit, we're going to give up and return nothing. And again, return is bad here, right? This isn't actually exiting the function on its own. This is exiting the function because it's like the end of the control flow. There's going to be nothing after this case statement. Otherwise, if it wasn't quit, we're going to try parsing it. So parse the line. And then we want to inspect the parse result because maybe it failed. So nested case statements, woo. So if it failed, we have a parse error. And what are we going to do? We're going to print the error and then REPL read. So again, this operator means do the thing on the left and then ignore the result and do the thing on the right. So print is kind of like putString, but it's a little bit more general. So putString absolutely has to take a string as its argument. Print uses show, which we talked about last week. So things that can be shown, there's a function called show, takes them and turns them into a string. Print does that, so it converts the thing to a string, and then it calls putString line. So it just drops that string into the terminal and then puts a new line at the end. So if we have a parse error, we want to print the parse error and then forget the result of print, because you can see down there at the bottom of the editor, hopefully, its return type is unit, and units aren't useful. So we're going to forget the unit and then read instead. And sorry, just in case I didn't mention, IO is short for input output. So exactly what you'd expect. That's the type that represents interactions with the user. Nope, that was right. Okay. So if it didn't fail, we have an expression, and that's what we were looking for. So we return just of the expression. Okay, this is our reader. Okay, so the next thing is evaluating. I'm just going to make this nice little convenience type so that I don't have to write it repeatedly. So the result of an evaluation is the type from type checking. And remember, our type checker never fails. So there's no maybes or eithers here. And then a result value from the evaluation. As the language gets more complicated, it will be possible for type checking to fail. And so this result type will get a little bit more interesting. That's part of why I'm defining a synonym now. It's because otherwise I'm going to have to make changes all over the place. Okay, and what does eval do? Well, you have an expression, you type check it, and you evaluate it. And that's it. There's nothing else to do. Okay. And then the next thing is print it. How do you turn a result into a string? You could mess with this and try other representations if you want. I'm going to use a relatively normal, in ML at least, representation. You put the value, you put a colon, and then you put the type. These are going to use the show functions that were derived all the way up here. So this one, deriving show, deriving value. I'll show you what these look like in a minute. They don't look good. So if you're interested as an exercise, you could make them look better. And the way that you would do that is you would write instance show type where, and then you would put a definition for show here. So you would say show tyconst whatever, probably just equals the string because this would look okay. In a real interpreter, you actually wouldn't define a show instance. You would do a whole bunch of other things because it turns out the derived show instances are actually useful for debugging and you want to keep them. But for our purposes, we don't really care. So, okay, we have all the parts of the REPL. We have read, eval. This is kind of print. It actually just turns it into a string, but whatever. So now we just need the loop part. So no useful results. So we just make it unit. And what do? We try and get an expression from REPL read. You'll notice I called this mexp instead of exp. This is a pretty normal style thing. I would have called it exp, but it's a maybe expression. And so the convention is just to stick m in front because of the maybe. And then we inspect it. What do we have? If we have nothing, that means the user wanted to quit, so we shouldn't do anything. If we have just of an expression, yeah, sure, let's use do here again. So nested do block. This works exactly like you'd think. We put string, the result of pretty, the result of eval. Good so far. And then we REPL again. So this makes the loop happen. This says do a thing. Whoops. This says do a thing and then call REPL again. So that this just turns into a while loop basically. This is more or less while REPL read is returning just put string line REPL pretty REPL eval. And then as soon as REPL read returns nothing, you quit. You could actually import. There's a library called. Actually, I don't remember what it's called, but it has a bunch of useful looping functions in it. And one of those functions is called whilem. So you could write this with while if you wanted. I'm not going to do that because I don't want to pull in a dependency just for one function. I don't really have extra time. Otherwise, actually, maybe I'd write it because that's a good exercise. But OK. So this is actually everything. The only other thing is you want to define the name main. Main is just our REPL. So Haskell's like most languages, it starts execution at main. And so again, if I stop sharing so that I can pull up my terminal as well. Share the whole screen. Like this. OK, so we can quit. Oh, actually, I guess I shouldn't have done that. Reload it. OK. So start main. So this is our prompt, lambda right arrow. And we can just put constants here. So we put 0, we get int val 0, and its type is tyconstant, right? I said these are ugly. We can put true, we'll get bool val true. We can put false, we can put unit, and we can put a floating point number, like 0.5. And so this is a complete interpreter for a language that is completely useless. But that was a goal. Actually managed to get through all of that in an hour, almost exactly an hour, dang. So yeah, if anybody has any questions about all of that, I kind of did the REPL really quickly, so maybe something was confusing. Let me know. I'll put the link to the reference code, which I think actually ended up being almost identical to what I wrote today in the Slack. So if you want to look at it again, it'll still be there. And then we should add strings at some point. Strings are a little bit harder to parse, so I didn't want to do that while at the same time as introducing all of this other syntax for parsing. The reason strings are a little bit harder to parse is because they have like a designated start and end, and then there's like escape characters inside the string that let you get around the string being over, and it's like kind of a mess. So maybe we can do that next week. Or actually, if anybody is just like interested and wants to try parsing strings, I introduced enough of the syntax and all of the functions that you would actually need to do it. So give it a shot if you think you have something that works posted in Slack. Actually, similarly, if somebody wants to try writing, a better REPL pretty function that looks better than this garbage, try that too, post it in Slack. And then, yeah, probably the next thing we'll add to the language is like simple variables. Not sure, we'll figure it out. Variables start getting a little bit more interesting. So now suddenly there's actually some type inferencing work to do. There's a little bit of evaluation work to do. We need an environment like we needed last week. And yeah, actually, what you'll see once we get there is we actually need two environments. So we need a local environment while evaluating a single expression. And then we also need a global environment of the names that have been bound inside the interpreter. And then evaluation of an expression starts by copying the global environment and using that as the starting point for the local environment. So, there's kind of this play in an interpreter between the REPL and the actual evaluator that you really don't see when you're doing something like simply typed lambda calculus. But you would see in any real language, right? Like a Python interpreter has this kind of interplay, actually at a much higher level, right? Python interpreters doing some more complicated things too. But yeah, so we're still a little bit away from having functions in our language. That's when the language actually gets interesting. But yeah. Oh, I guess the other thing, I didn't say this while I was introducing the language at the start. The picoML that we're basing this off of doesn't have a way to define new types. So all you get is ints, bools, units, floats, functions, whatever. We're hoping, if we can figure it out, to have a system for this language for defining new types, because that's basically an integral part of actually making a language. And I would feel like I was cheating you guys if I showed you how to make an interpreter and didn't show you how to do that. So yeah, okay, I think that's everything now. So if anybody has any questions or comments or concerns, speak up. Otherwise, I think that's it.
I have a question. I still kind of don't understand why was tie const, why'd you use a string instead of the enum?
Oh, instead of making an enum type like int tie, float tie, bool tie, unit tie?
Yeah.
Yeah, so actually the reason is because we want to have ways to make new types. And so if you're running the interpreter and you write a line that makes, a new type called foo, right? There's no way in Haskell to add a case to like some const tie enum. There's no way to add a case at runtime. And so I wouldn't have a way to represent the name of your foo type in the interpreter.
Okay.
So using a string lets me just pretend that I have access to all of the names that could possibly exist. I would just say tie const foo and move on with my life.
Could you just do like the types and then just like, custom type as the last enum?
Yeah, you could do that. It's not normal to do that because it makes, so this is, I guess, a Haskell specific thing. Usually when people write interpreters in Haskell, they wouldn't do that because it means you're adding more cases of code that are identical, right? You have a case for your int type and your bool type and your float type, and they're all exactly identical to the case that just has a generic name anyway. It would be slightly safer, right? Like in terms of the type system, the Haskell type system would be able to, guarantee that at least if you're using one of the enum types, you actually have a type that exists, right? So for example, in this system, it's possible to create a value that makes no sense, right? I could say tie const foo, and that makes no sense. There are no things of type foo in this language. So if you used an enum, the type system, or I guess it's more like the value system, but the type system would be able to guarantee that your types make sense. But that turns out to not really be useful anyway, because as soon as you have custom types, you can, it will always be possible to create types that don't make sense. And the type system can't save you from that. So there's no reason going halfway.
Okay, that makes sense.
That was a good question though. Yeah, I specifically didn't mention that at the start because I hadn't talked about adding new types yet, but that is a goal. If you were working in a language where you didn't have a way for the user to define new types, like Lisp, for example, I think Lisp with no extensions, there's no way to make new types. Then you would use an enum type. So like in Lisp, the only types are number, pair, Boolean, symbol. I think there's one more that I'm forgetting, string. And yeah, if you want to make a more complicated type, you would basically just make a tree using pairs of pairs. And then you would use what's called like a magic token. So you would put a symbol somewhere in that tree that says like, this tree is my type. And then all of your functions that process this tree would make sure that it has that symbol in the right place. And like, that works, but it's super not cool, right? There's no type system that's making sure that you're only passing my trees to functions that expect my trees. And so you end up with errors at runtime. Errors at runtime are bad. But yeah, so you know, there is like actually a design space here. When you're designing a new language and you're writing an interpreter for it, you wouldn't always put string here. In our case, we want to. But yeah, you wouldn't always do it. For some reason, in the picoML interpreter that they write in the class, they actually do put string here, even though they don't have a way to define new types. And so they arguably shouldn't, but they do.
Okay, cool.
And I guess, I mean, part of the reason to do that is, like I said earlier, otherwise you're just duplicating code, right? You have a bunch of identical cases. Any other questions? No? Okay.
Cool. Well, thanks, Max, and thanks everyone for coming. We'll do more interpreter things next week. At least that's the plan so far. So let me